One of the examples that we talked about was the Michaelis-Menten equation, which is commonly used to look at enzymatic reactions, and that's the equation written down there. V is the reaction rate. Vm is actually, it says down here, there's actually an error here. That shouldn't be maximum initial reaction rate. That should be maximum possible reaction rate. And something's gone strange. Okay. S is the concentration. And so the reaction rate depends on the concentration. And Ks is basically, it's constant. It's known as the half saturation constant for reasons that we'll have a look at in a minute. So this equation here, quite clearly, there's an S on the top and there's an S on the bottom. It's a non-linear equation, okay? But we can linearize this equation in order to do a best fit straight line, and that's what we're actually going to do in a minute. Okay. There is also a second order model. The second order model looks almost exactly the same as the first order model, except now we have S squared, and our coefficient here is also squared, but effectively it looks pretty much the same. And if we actually just plot these two things on a curve, Vm here is the maximum concentration that we can get to, maximum reaction rate, sorry, that's possible. We can see that the first order, the blue curve down here, is pretty straight, but there's this interesting kind of like little, I guess, kink in the second order one, and the thing goes up. So the question is, if you have some experimental data, which of these reaction equations describes your reaction best? Are you going to do some kind of curve fitting to actually to see what the case is there? Okay, so we've extracted some data, and we now want to look at whether this data here that we've measured is fitted best by the first order model or fitted best by the second order model. And we can use this is the saturation growth rate conversion, taking this saturation growth rate model to linearize it. And it's really simple. And what I, speaking to the demonstrators yesterday, at least a few people had some issues with exactly how to convert this into a linear system. Don't try and remember the conversion formula. Remember how to do it. Because if you can remember how to do it, you can do it and get it right every time. So the simple way of looking at this one is, well, we've got an x on the top and an x on the bottom, but the x up the top here is by itself. So if we can invert this thing, we can end up just dividing by x. At the moment, we're dividing by a coefficient plus x, and it's pretty messy. So if we just invert this whole thing, 1 on y equals that to the minus 1, then it's very easy to show that you end up with this equation here. Okay, remember how to do that. Don't remember, oh geez, the beta 3 on top is the alpha 3 on top, how do I do this? Just remember how to actually do it rather than remembering the formula. And I recommend that that's probably a good approach for everything. Remember the simple stuff. Remember how to do it. Don't try and, remember the concepts behind it. Don't try and remember the detail, because you can always figure out the detail. What we've got now is we've started off with this non-linear model. We've inverted it. We've now got a linear model, but the linear model looks a little bit different because now our variables are 1 on y and 1 on x. Okay, so we're actually going to treat that as our normal y and x. Okay, so don't sort of get too confused by that. Just say, okay, this is our new variable. We can call it anything we like. We call it p. We call this one q, and then do a curve fit for that. Okay, so we end up doing that. Again, we end up with just what we had on the last page now with this particular equation here. That's our new y. That's our new s. Okay, and when we do a curve fit to this thing here, what we're trying to find is these two parameters there. We're trying to find 1 on Vm and Ks on Vm. So if we do a linear fit to 1 on V and 1 on S, we get the parameters coming out of the curve fit. We then got to convert those back to Vm and Ks, okay? Because what we've actually got is we've found these two things here. We actually haven't found the inverse of the relationship, the division of the two of them. Similarly, with the second order model, we do exactly the same thing. We take the inverse of both sides, and we end up with two new variables. Our new y is equal to 1 on V, and our new x is 1 on s squared. Okay? That's why you don't want to try and remember the formula between these things, because if I give you something where there's an s cubed down here, or an s to the fifth, you won't have seen it before. But if you can remember just to invert these things, the same with the power law and the same with the exponential. You're going to take logs there. Okay? And the power law and the exponential, you'll end up with two variables. In one case, you'll have a log x and a log y. In the other case, you won't. You only have a log y. Okay, so what we can now do is, once we've got both of these things here, we can do least squares fitting using standard linear regression. Now, what we did in lecture 15 was we went through and did the linear regression the hard way. We did all those sums, we divided things together, and we calculated the coefficients. And remember, I told you, you don't need to remember those formula. Those will always be given to you because they're too complex to remember. But you've also got to pay careful attention to what the formula is actually saying. Is it the sum of x's multiplied by the sum of y's, or is it the sum of x times y? Okay, you just need to look at the formula and interpret them correctly. But there's another way to actually do this curve fit. We don't actually have to use those formula. What we can do, at least if we're doing it in MATLAB, is we can use MATLAB to do it for us. And the way in which we do that is we use polyfit. Okay, there's also a little bit of confusion about exactly what polyfit is doing and what it's giving you back. Okay, so let's just spend a little bit of time looking at that. So polyfit is you're passing in some x values and some y values, they're corresponding x-y pairs. You're telling it what degree polynomial you want to fit. In this case, I want to fit a straight line. So this is why this is equivalent to doing that linear regression. We're telling polyfit, I just want a straight line. And what polyfit is going to do, it's going to go away and do a best fit to a straight line. If we'd put in 5 in there, you'd try and fit a quintic polynomial in a best fit kind of sense. But we're not doing it. We're putting in 1. We're saying, fit me a straight line that's the best fit. It's ultimately doing exactly the same thing that you would do if you did all those sums and calculated the coefficients yourself. So what polyfit gives you back is this vector of coefficients. And that vector of coefficients tell you what powers are in the best fit curve. And remember, the thing about polyfit in MATLAB is P1 is the coefficient of the highest order power. It's not the coefficient of x to the 1. So they're sort of swapped around the other way. So in this particular case, it's going to be P1x plus P2. That's effectively what P1's returning you back. It's just these coefficients, P1 and P2. You can actually go away and then do this by hand if you want to, but the smart way of doing it is actually to use polyval. And I think that's on the next slide. Yeah, so let's just quickly look at what we've done here. So what we've done to actually solve this thing here is we said, okay, this is our new y variable, so we're going to set y equal to 1 on v. This is our new x variable, so we're going to set x, our new x variable, equal to 1 on s. Okay, we're then just going to put those two things, so we're putting 1 on v and 1 on s into polyfit, doing the curve fitting, and then I said, okay, we've got these coefficients P1 and P2, that's P1, and that's P2, so we've then got to get back our Vm and our Ks. Okay, so we just need just a simple formula between the way those two things are related to each other. Similarly, we'll do something simple with something very, very similar with the second order model. Okay, once we've got those coefficients in the P, so P is equal to polyfit, we can then use them in polyval to calculate the value anywhere we like. So the way polyval works is we pass in that coefficient array and we pass in the value of x where we want the function to be calculated. And it's as simple as that. You don't have to do anything complex. Polyfit calculates the coefficients. Polyval actually calculates the value at some x value that you give it. Or if you pass in a vector of x points, it'll calculate the value of the polynomial there. Okay, just another thing worth pointing out on this thing here is the use of this command subplot. It allows you to plot multiple plots in a single figure. Okay, and so what we're basically saying when we're saying subplot 2, 1, it means we want 2 rows of figures, 1 column of figures, and this is going to be the first one. Okay, likewise, For the next plot, subplot 212, I want 2 rows of figures, 1 column of figures, and this is going to be the second one. And the ordering goes along the rows and then down the columns. Okay, so let's just have a look at this. So let's just separate those out. Okay, so this is what I was saying about the 2 plots using subplot. What we've done here is we've plotted 1 on V versus 1 on S, and we can see that we're fitting a straight line to 1 on V versus 1 on S, and here we're plotting 1 on V versus 1 on S squared. So this is the first order model, that's the second order model. And we can kind of see, even by eye in this linear space, we can kind of see that this one looks like it's a little bit better. If we actually then convert back to V and S, which is really what we're trying to find, we can plot exactly the same things, and we can see that the first order model over this range from 0 to 9 gives this red straight line here, and the second order model fits much better. Okay, we can just eyeball that and see it. I also said you can't just eyeball things and make your assumptions on that. You also then need to go away and calculate your coefficient of determination to actually get some quantitative measure. And you've got to go back and look at what the results are telling you. Are the results physically meaningful, or is there something fundamentally physically flawed with them? Now, in this case here, both of these look fine. There's nothing physical that suggests one of them is wrong. So both of them are potentially okay fits. It's just clear that the green one works better. Okay, so the other example that we had a very brief look at, and I'm not going to go into any detail on this one again today, but was modelling a rocket's trajectory when we knew that in various different times throughout the trajectory, the behaviour of the rocket was very, very different. Okay, so in the early times from 0 to 10, it was doing this. Then between times 10 and 20, the velocity was changing like this. Times 20 after 30. We don't need to worry about the otherwise. And so if we actually want to go and plot to see what that looks like, it's some curve that looks like this. So it starts off doing nothing, then all of a sudden the rocket engines fire, the velocity gets higher and higher and higher, then for whatever reason it gets a little bit lower, then we've got another spike going up here, and then gradually it sort of slows down and does this. So if we tried to use polyfit to fit a third order polynomial to this, we end up with this blue curve here. Okay, now it captures a few of the really coarse, crude parts of the behaviour here, but effectively all of the details completely wiped out. So it's nothing to do with the peak here, there's nothing to do with that. It over-predicts here, it under-predicts there, it's a pretty lousy fit. So the next thing you might think of, well, third order, clearly it's not going to get all those wiggles because the third order's only got 2 inflection points. Maybe if we fit a higher order polynomial, we'll end up with something that's better. Let's fit a 15th order polynomial. Well, we've actually got a better fit, there's no doubt about that. We're picking up more of this stuff, but we're still not picking up this. That's completely disappeared, and you know, potentially that's the most important part of the entire analysis. But we've also got some weird stuff going on down here. We've got these oscillations down the bottom there, which are clearly unphysical because the rocket engines don't fire till there. So it's clear that this curve fitting that we've done here is not a very good way of doing it. So the simple thing to look at this and say, well, it doesn't make sense to fit a high order polynomial. It doesn't make sense to fit a single function to this data. The other thing that you need to take away from this is that it's always a bad idea to fit a high order polynomial. Okay, some of the examples I showed on Friday, you can actually see that even if we had a function that looked like this and we fitted a polynomial to it and maybe it went through all 5 points, in other words, it was a perfect fit at the data points we gave it, the actual function was doing something that looked like this. So whilst it matched the data points, it was doing a really bad job everywhere else. Okay. Now, if we've only got these 5 data points, we don't know that. We don't know it's doing a bad job everywhere else. But as a basic rule, you'd never fit anything more than a 3rd or perhaps 4th order polynomial to points. I'd basically suggest to keep it at a cubic. So what's the way around this one? The way around this one is to split your domain up into different segments. So there's one segment ends there, one ends there, one ends there, one ends there, one ends there, and then fit polynomials to each one of them individually. Okay, now that's a far more tedious thing to do because you've got to know, well, where do I have to split this up? Okay, you've got to make that choice. There's no simple way of actually telling MATLAB, oh yeah, split it up where it looks sensible. MATLAB can't do that. You've got to be the one that figures out where you need to split things up. Okay, so that's that lecture done. This card. 16, okay, so let's come to today's lecture. Any questions on any of that stuff about polyfit, curve fitting, linear regression, anything like that before we move on? No? Okay, I'll assume that you understand it all perfectly. Okay, so what today's lecture is about numerical integration. Okay, numerical integration is really one of the most fundamental numerical things that you're going to have to do. It comes up in kind of simple problems in calculating answers to various things, but it also comes up solutions of ordinary differential equations, solution of partial differential equations, etc. Okay, I don't think I need to recap root finding yet again, do I? Everyone here's got all that sort of sorted out now? Okay, I don't really want to do it because we'll run out of time again. Optimization might just be very briefly worth mentioning. Remembering that optimization effectively means finding the root of the derivative of something. Okay, but you've got to remember you've got to find the correct root, and you've got to read the question that you're given as well to figure out whether exactly what it is that you've been given. Okay, we've been through linear regression. We just did some examples of polyfit and polyval, so we don't need to go through that again. So the question is, what is integration? What are you actually doing when you integrate something? Well, let's take a look at the simplest example that we can come up with. We've got some function f, that's this solid curve here. We've got 2 limits, a and b, and we're trying to find the area underneath that curve. In other words, between the x-axis and the curve. Effectively, that's what integration is. It's a pretty sort of simple concept. You're just trying to find the area underneath something. Of course, integration in practice can be a lot trickier than that. This is a nice, simple, one-dimensional integration. What happens if you've got a function with x and y and you're trying to find the volume under it? It becomes a little bit trickier. If you've got some 5-dimensional function, you're trying to find some kind of phase space integral of what's going on there, things become much trickier. In particular, the limits of integration become extremely difficult. Okay, so the 2 main uses of integration in engineering are effectively summing things up or averaging quantities. Okay, and we'll have a look at a few examples on the next page and also here. So, for example, calculating land area from a satellite image. And in actual fact, you'll be doing something very similar to this in your assignment. Okay, effectively, you'll be doing an integral, looking at images and trying to figure out how much stuff is inside a certain boundary and how much isn't. If you have some complex shape, for example, you might want to know what the surface area of your metal parts are, because that's going to tell you something about the heat transfer. But you need to do an integral to calculate what that surface area is. Determining the volume of a pool of liquid, and this is a good example. In actual fact, you might be determining the volume that's going to be inside a dam you're going to be building. So you build up a dam wall, you've got all this interesting topography behind the dam. How do you know how much water is going to be inside the dam? You need to do an integral. Getting total force of wind on a tall building, so if you have some measurements, maybe some spot measurements, how can you extend that out and integrate that force over the entire surface of the building to figure out what the bending moment's going to be? How strong does the building have to be? what kind of vibrational characteristics is it going to have if you put forces up there. Estimating energy in electrical circuits, averaging things like temperature, velocity, current, voltage, stress, and a whole bunch of things like that. They'll crop up in your engineering degrees, and also when you become an engineer, they'll crop up there all the time as well. You two, if you want to talk, that's fine, but could you do it outside? It's kind of really off-putting for me. Okay? Okay, so some examples. Well, the examples are pretty much what we covered yesterday. Calculating mean rainfall, calculating the simple integral underneath a function. There's the case here of certain topography. We're actually trying to calculate how much water is underneath this thing here, but perhaps this topography then changes as we go around. So this is the plan view. That's the elevation. You've then got a very complicated integral. How do you actually figure out what the boundaries are, the limits of your integral? Likewise, force on a tall building. Okay, so let's go back to our favourite character, our bungee jumper. The formula that describes his velocity when he's being slowed by air friction and also being accelerated by gravity is given by this function here. Okay, it's an analytic function, we know what it is. We can take that and we can figure out, well, if we know what the bungee jumper's velocity is at every time, we can also calculate what the position of the bungee jumper is. Okay, we do that basically by doing an integral. Okay, so for example, how far has he fallen? In particular, how close is he to the ground? How much time has he got to do something about his predicament? So what we can do is we can integrate the velocity over time to find his displacement, his position. And this is a pretty simple example, but what basically that is saying is that, okay, if we basically start off with dz dt is equal to the velocity, because it is, and we integrate both sides of this with respect to time, well, the integral of dz dt with respect to t is just z, that's where the z comes from. The integral on the right-hand side is integral from 0 to whatever time we want, v of t, so that's where the right-hand side comes from. So z is equal to the integral of velocity with respect to time. We, in this case, have an analytic expression for the velocity, so we just plug that straight into the right-hand side. And even better in this case, you can actually integrate that analytically. So the integral of tan h of this thing is just log cosh with a few other constants scattered about. So in this particular case, it's actually pretty easy for us. We can calculate what his position is at any time using this formula here. That doesn't happen very often. Usually in most of the engineering problems you're going to be looking at, you're not going to have a nice analytic function like that. It's going to be something that's maybe come from experimental data. It's something where there is an analytic form, but it's impossible to integrate because there just isn't a solution to it. So you're going to have to do things numerically, sorry. So integration in some sense is like adding things up. Okay, so let's this sort of assumes that you can do it numerically, and of course you can do it numerically, but let's have a look at this really, really simple function. The function is f is equal to 2. F of x is equal to 2. It's a constant function. And we want to integrate it from a to b. Well, it's not that hard. In actual fact, that's just twice times b minus a. So the integral is equal to twice times b minus a. Okay, that's really simple. You don't often have to integrate straight line functions. You don't have constant functions. This is even simpler than a straight line. It's just a constant. But if you have different function values at the end, perhaps you can do an approximation to that integral by fitting what's called a trapezoid. So if our function does something like that, start the end point a bit, we take the function values at the corner points there, and we fit a straight line between them, and then say, okay, the area of this integral is approximately equal to the function value at 1 plus the function value at 2 divided by 2, there's the 1/2, multiplied by that distance. In the previous slide that was b times a, so that thing there would be b minus a. Okay. This effectively is the trapezoidal rule. What you're doing is you're looking at a function, you've got the endpoint values, they can be analytic values, or they could be values that you've measured experimentally, but you know what they are, you just plug them into a formula like that and say, okay, this is an approximation to my integral. It's not necessarily a great approximation, but it's an approximation. So let's have a look at what the problem is if we do some of those, make some of those kinds of assumptions. Well, let's have a look at a case here where we've got a function that varies a reasonable amount. We know the function value here, we know the function value there, we draw a straight line, and we approximate the integral. We should actually have an approximately equal sign there. I is approximately equal to the width multiplied by the average of the two function values. So I think you can see, just sort of like eyeballing it, there's all this region up here that's not included in the integral. So the further away from a straight line your function is, the worse this approximation is going to be. There are ways of getting around this, of course. But let's have a look at how we'd actually do this in MATLAB in a really simple script. So we're just going to have a look at this function here, minus x squared plus 3x plus 80. That's actually the function on the previous page. We're going to set an interval from 0 to 10, and we're just going to set x to be equal to 0 to 10 with interval increments of 1. We plot that function here. Another thing worth noticing is that axis function here. MATLAB, if you don't say anything about the axes, it'll go away and try and make its best guess as to what axes you want. Sometimes it does a really good job, sometimes it doesn't. For whatever reason, you might want a series of plots to have exactly the same axis range. Okay, the way in which you do that is you use this axis function. So you say, I want my x-axis to go from A to B, I want my y-axis to go from 0 to the maximum value of f of x plus 10. You want a bit of extra space at the top. Okay, so this is just a little bit of MATLAB thing which allows you to make your plots look more uniform, if that's something that's important. So the trapezoidal rule is about as simple as you can imagine, given the formula that we had on the previous page. The estimate is just equal to the length of the interval, in other words, that b minus a, that's how wide our trapezoid is, times 1/2 sum of the end function values. And that's it. I don't know whether I can say any more on this because it's really that simple. Let's look at an even more extreme example of where the trapezoidal rule might fall down. Let's have a look at this function here. It's given by about there, so f of x is 0.2 plus 25x minus etc. And we've got function values at 0, we've got function value at 0.8. And we fit our little trapezoid to it. It's this bottom bit down here. And all this top stuff just disappears out of our estimate. Okay. When you're using things like the trapezoidal rule, again, it's good, if you can, to plot the function. What does the function look like? Is it going to make sense to use an interval that's this big, or is this really going to give me huge errors? Because if you just blindly go away and do it, you will never know what errors are. Well, there are ways of finding out the errors, but if you don't look for them, you'll never know what the errors are going to be. So you need to have a look at what you're doing and what you're trying to integrate to actually make sure that what you're trying to do makes sense. So we can actually go away and do a rigorous analysis on this because we have the functional form of the error, functional form of the function that we're trying to integrate, and so we can analytically integrate that. And if we analytically integrate that, we get the value of the integral to be 1.64. If we look at our trapezoidal rule result, we got 0.17, so there's about a factor of 10 difference. Now recall what the truncation error is. Truncation error is the difference between the exact answer and your approximate numerical solution. So if we plug those two values in, we see that our truncation error, unsurprisingly, is this large number here, 1.46, and the percentage truncation error is just that value there divided by the exact answer multiplied by 100. So we can see that our error is 90%. So it's enormous. And this would be an absolutely hopeless thing to do in practice. So truncation error is really big. That's really good to us. We can do that because we know what the analytic solution is. But as I keep on saying, most of the time you've got no idea what the analytic solution is, or there isn't an analytic solution. It's some kind of experimental measurement, or it's some kind of numerical computation that you've done, and that's where you've got your information from. You can't put it in. So how can we look at our results and actually try and say, well, is the error big, is the error small? Do I know I'm doing a good job, or am I doing a really bad job? It turns out that, yes, you can say some things about this. It turns out, and we're not going to go into this in this course, but it turns out that the truncation error for the trapezoidal rule can be written like this. The exact error is equal to 1/12 the second derivative of our function that we're integrating, evaluated at some point, and we'll come back to that in a minute, multiplied by the width of the interval cubed. Okay? This value of psi here has to lie between those two bounds, the left bound and the right bound. But the question is, we don't know what that point psi is. This basically says is somewhere in that interval there'll be a point that if you could plug this thing in here, you'll get the exact integral. Okay, where f double dash is the second derivative. The most important thing about this formula here, I think you can see, is that it implies that functions where the second derivative is big, in other words, where the slope is changing, will have large errors if you use the trapezoidal rule. And I think if we went back to the previous function where we had the function that went up and did something like that, we can see here the second derivative is large. That slope is changing. It's very, very positive, then it gets very, very negative over a fairly short range. So this value is large, so therefore we expect the truncation error to be large. It also, the other thing that's kind of like obvious coming out of this, if the second derivative is 0, then we know that we've got no error at all. So what does it mean for the second derivative to be 0? It means you've got a straight line. So the trapezoidal rule works exactly for a straight line, but that's hardly surprising because the trapezoidal rule effectively is fitting a straight line between 2 points. So we haven't really learnt anything from that, but at least it's internally consistent. Okay, so this is the function that we've been having a look at on the previous page. This is our error estimate equation here. We can quite easily analytically again take the second derivative here. Now I said before that this thing gives you an estimate of the error if you knew what this point zeta was or psi was. We don't. So what are we going to do to actually say anything about the error here? Well, in actual fact, if we take the mean value of f double dash, it's not going to give us a correct answer, but it's going to give us something that's the right order of magnitude. And I think one of the things that I'll try and get across in the rest of the course is that it's almost never possible to get exact estimates of error when you're dealing with things computationally. All you can do is get estimates of what's known as the order of the error. In other words, is the error big? Is the error small? Is it 10 to the 4? Is it 10 to the minus 6? But you can't tell whether it's 3 by 10 to the minus 6 or 8 by 10 to the minus 6. In fact, from the point of view of numerical analysis, those two things are the same. It's about that big. Okay, so nearly nothing we do here in numerical will we get an exact estimate of the error. It's only when we have the analytic expression. So if we actually plug this into this equation here, average over the range 0 to 0.8, divide by that to get the average, we end up with an error estimate that's about 2.5. And if you actually go back previously, the exact error was about 1.5. Okay, now you can say 2.56, nothing like 1.46, they're completely different. Well, in actual fact, they're not completely different, they're the same order. Now, if this thing was 200, then I'd say, yeah, they're completely different. Or if this was 10 to the minus 4, I'd say, yeah, they're completely different, something's wrong here. But they're not, they're the same sort of magnitude, 1, 2, pretty much the same. Remember here, we're just talking about errors. And we anticipate that these errors are generally speaking, are going to be much smaller than the thing that we're actually looking at. So even if the error is 1, it might be that the force is 10 to the 8th. And an error of 1 in a force of 10 to the 8th is going to make absolutely no difference at all if you're designing something. But an error of 1, when the force is 1, well, that's massive. That's something you've then got to worry about. Okay, so how can we improve the order of accuracy of the trapezoidal rule? We've seen if we fit one trapezoid to a function, I mean, we can end up with incredibly bad results, especially if there's high curvature. That second derivative has got a large value which is non-zero. Well, it sort of seems like the most obvious thing to do would be to say, well, let's not just fit one trapezoid, let's fit multiple trapezoids. And as we make these trapezoids smaller, hopefully, we won't end up with the same problems. Okay, so if we've got our function going from x1 to x3, we could maybe fit 3 trapezoids there. We've got the function values in the center. And effectively, we're drawing 2 separate straight lines, one between those 2 points and one between those 2 points. Okay, and, well, in actual fact, the very, very simplest way of doing this integral is actually not to use trapezoids at all. It's to use rectangles. Okay, so that's an even simpler way of doing things. And the area of the rectangle, of course, is just going to be h times the function value at that particular point. And so we could then do that for the 3 of them and sum them up. Okay, and then we make an estimate of the total integral as being the sum of those three rectangles. You can do that, and it'll give you an okay answer. It'll give you something that's approximating it, especially if you make, we've only got 3 intervals here, but if you make that number of intervals very large, you actually start getting potentially acceptable answers. But it's not a very efficient way of doing it, okay, because it's not very accurate. Now, if we are actually integrating from x1 to x3, rather than from this point here to this point here, these bits here actually aren't part of our integral at all. We actually don't want them. Okay, so if we chop them out, we then come up with a slightly different value, the variation on the formula that we had previously. It's equal to half this rectangle plus all of that rectangle plus half of that rectangle. Okay, so what we're really trying to do is integrate from here to here. And then, well, why stop at 3 segments? Let's put in 10 segments. We're just going to take half of that one and half of that one, but all of those ones there. So this is splitting things up into smaller and smaller increments. In fact, in the limit, as this step size here, in the limit as h goes to 0, we get that smaller and smaller and smaller. This sum will actually approach the integral. So in other words, if we could keep on going forever, we would actually end up with an exact representation of the integral. There would be no error. Of course, you can't keep on going forever. Okay. I think you can see that as we make these things smaller, the errors, these tiny little rectangles in here, they're getting smaller and smaller and smaller. So, and likewise, the function, which at a large scale might be doing this, if we zoom in and look at a tiny bit, it's almost a straight line. Not quite, there'll be some small deviations. The more we zoom in, the closer and closer that little segment looks like a straight line. That's why the errors appear to be, that's why the errors are getting smaller. So what we can also do, so that was a really simple one where we just looked at rectangles, we didn't look at trapezoids at all. We can also apply the trapezoidal rule using multiple segments. So what we're doing now is we're going to integrate from x1 to x3. We're going to fit straight lines to these bits here. Okay, so the bit that we cut, we don't get in the integral. In this first thing is just this little bit, this little red triangle here. We don't, we don't include that in our integral, whereas we had done previously when we were just using rectangles. This is tedious. Okay, likewise, We actually include this as part of our integral now, whereas we didn't previously. And I hope I don't have to zip through. Yeah, okay. So the first trapezoid then becomes this one here, okay, where we've chopped off this bit, but we've added this bit in. So in some ways, these, you can see that these maybe sort of cancel each other out a bit. Obviously, they're not going to do it exactly, but you can see why this is going to be an improvement over just doing the rectangles. Likewise, if we then do the next one. Oh, gee, okay, this is slow. So this is just the area of this rectangle in here. x2 minus x1, that's the width, multiplied by the average of the function values of the 2 points. Okay, if we keep on going through that process, we end up with something that looks like this. We have an integral that we're trying to do from x1 to xn, and we split it up into a whole bunch of little segments. So an integral from x1 to x2, integral from x2 to x3, etc., integral from xn minus 1 to xn. Now, worth mentioning, this is just a bit of an aside, but it's an important aside, if you have n data points, you will have n minus 1 segments. Okay, so that's data point 1, 2, 3, 4. This will be segment 1, segment 2, segment 3. So you've always got one less segment than you have data points. Okay, and the spacing, if you make the spacing even, is going to be equal to b minus a divided by the number of points minus 1. Okay, that's how big each of these segments is going to be. And this is a trap that many people fall into. They divide by n, and they get things just a little bit wrong. Okay, what it does mean is that your answers, when the demonstrators come to have a look at them, won't be correct. So make sure that you use n minus 1. So getting back to the integral then, we split this integral up into a whole series of things. We then calculate each one of these integrals using the trapezoidal rule. So the first integral is the width, which is x2 minus x1, multiplied by the average of the 2 function values, plus, etc., etc. Now, if we have split things up so that the step sizes are uniform between each of these different pairs of points, then this step size here is the same as this step size here, is the same as that step size there, and we're just going to call them h. That's the width. So we can take this h out of this factor. In fact, we can actually take an h on 2 out, and we end up with this function down here, or this expression down here. The trapezoidal rule estimate of an integral where we have n points, and h is the step size, which is b minus a divided by n minus 1, is just equal to h on 2 multiplied by, okay, let's have a look at this. The function value at the very first point, the function value at the very last point, plus twice the sum of the function values in the middle. And that just comes out from the fact that we've got the first, second, third, etc. This point here only ever appears in one of those trapezoids. But this point here occurs in the integral for this trapezoid and the integral for that trapezoid. This one here occurs in the integral for this one and this one. That's why there's a factor of 2 there. Okay, so this is what's known as the composite trapezoidal rule. Okay, it's composite because you're adding up multiple little bits. So if we actually go through the same example that we're looking at before, this expression here, remember where the error was 90%, really enormous, and we say, okay, I want to use 2 segments, so we're using 2 segments, that means we need 3 points, okay, and we're going to go from a is equal to 0 to b is equal to 0.8, and so obviously then the step size, if we make the points even, is going to be 0.4, just that distance divided by n minus 1. We calculate the function value at 0, the function value at 0.4, function value at 0.8. We plug it into this rule here, and we just add things up, and we get an answer that's 1.06. So if you recall, the previous solution was 1.6. We're still quite a long way away, but the error is getting much, much smaller now. The error's more like 30%. Remember, before it was 90%. So we've just added one extra point. And so what we're doing, because this function looked something like that, and previously we were integrating from this point to this point, now we've added one of these points in the middle. And so all of a sudden the trapezoids look like they're going to encompass a lot more of what's underneath this curve. So we've now got this, and we've got this bit here. That's why the error is reduced. And I think you can see if you added more points, you're typically going to get more and more of that error, or more and more of that integral correctly in that thing. So let's have a look at what happens if we do when we do 4 segments. I'm not going to go through in this, it's pretty straightforward. That's the answer that we get. What happens if we do 8 segments? The same thing. We're getting closer and closer all the time. So, well, in general, I'd say always, more segments produces more accurate integration results. But the trapezoidal rule is actually not that accurate a thing. It's a little bit inefficient, and so there are much better ways of doing it. However, it's something that's pretty straightforward to program, and let's go and have a look. Okay, so again, we've got our function. Does this? Yeah, it does. Okay, so we have the function that we're trying to integrate here. We're going to set a series of points. There's going to be 50 points going from 0 to 10. Is that going to be right? Yep. Okay, and the step size is going to, so it's going to be 50. It's going to be 51 points, but 50 intervals with the lin space here. So our step size is actually h is equal to 0.1. I recommend that if you're coding up something like this, that you don't do it the way it's been done here. I would make this 50 here some variable that you chose, say n, and set n is equal to 50, and in fact I'd set this being, x start, and this being x end, or this being a and that being b, and then I'd calculate h. H is equal to b minus a divided by n minus 1. That way you can't get it wrong. Well, you can if you get the formula wrong, but if you go away and change your naught, or change your start point or your end point, or you change your number of points, you don't have to remember to do multiple things. So, and this is what I've told a few people who've come to see me, always try and make your MATLAB code look like the mathematics. And make things variables, not fixed. So what we've done here is this is hard fixed. We're saying h is equal to 0.1. So if I change this 10 to a 20, it's going to be wrong. Okay, so traps the unwary. Make your code look as much like the mathematics as possible. So we just go through here, and the function's not in here, unfortunately. So where is that? Oh no, sorry, here it is, right down here. So the integral estimate is equal to h on 2 times the function value at the first point, the function value at the end point, plus twice the sum of the function values in the middle. So this is really simple bit of code. This single line of MATLAB code performs an integration for you, provided you know the function values at the various different points. And if we run that, we can see these are all the trapezoids that we've got here, and we get a pretty good estimate of the integral. So the composite trapezoidal rule is 616.65. The exact answer is 616 2/3. So the error is very small. So we can actually get decent results out of this if we take enough intervals. Just a couple more things to say. So the way we've done it so far is that we've assumed that all the intervals are the same width. In actual fact, they don't have to be. There is nothing whatsoever in the composite trapezoidal rule that says you have to use even width intervals. Okay? Now, usually it's nicer to use them if you can, because it allows you to do other things more accurately as well. But often, you might have no control over when you get your experimental measurements. The time between them might vary. You might only be able to get measurements at different spatial locations. There's a whole bunch of reasons why you might not have even points. Having unequal segments is also useful if you know that something really is changing dramatically in a particular location or at a particular time. You can take much finer measurements there and try and capture what's going on, but you might not need so much data in other places where things are varying much more slowly. So there's actually advantages to having uneven data points. And basically, the rule looks identical. You're splitting it up into, You're splitting it up into a series of intervals. So x1 to xn goes from x1 to x2, x2 to x3, etc. But now x3 minus x2 is not equal to xn minus 1. So you need to keep these things out the front. Okay, that's the only difference between the uneven spacing and the even spacing. In the even spacing, this thing is just equal to an h, and you can pour it out the front. It's the same for all of the intervals. It's not for the case of uneven points. I think it's probably time for us to go. Have a look at that. Have a look at that example. It's pretty straightforward.